work. The capacity to do it. That is a more general definition. To do something, okay, to study, for example, for me to talk, okay, that requires energy, okay. Now, but here this chapter is dealing with not only defining energy, it's also defining how we measure energy. There are units, you know, as in chemistry or in any science, there are certain units to measure energies, right? So one of the common units that we're using is Argeta. What was the common unit that we measure energy? You left because you have some issues. Calorie, very good. Calorie, one of the units, and the other unit was joules. Joules. And then there is also certain values of calories and joules. Calories, sometimes you have food nutritional values, okay? The food nutritional values are measured in a different calories, okay? If you remember, we put a little bit different C, right? Which is a big C, okay? A big C refers to a calorie, right? And in fact, we also calculated about how much calorie we get from protein, how much calorie we get from fats, and how much calorie we get from carbohydrates, right? And then, for example, if you have 23 grams of fat or 26 grams of protein, and how much calorie it produces, and we know that 1 grams of protein generates about 4 calories, right? And then we can multiply that, and we know how much energy that we gain. We also discussed about this is a little bit different. Bigger? I don't even know where that is.
Oh, no, over there. All the way to the left. All the way to the left.
Oh, here? Okay, okay. Yeah, here you can see that a calorie is the amount of energy needed to raise the temperature of 1 gram by 1 degree centigrade. There is also some things that you'll be familiar with maybe in the lab, specific heat capacity. That's a little bit different than calories, specific heat capacity, which is C. It's again C, small c, okay? Specific heat capacity means, you know, how much energy can a substance absorb, okay? How much energy can a substance absorb is measured in specific heat capacity. Because different substances have different specific capacity. Like if you go to in Ocean City, for example, in summertime, you feel warm, or your feet will be burned when you touch the sun, but the water is still cold. Okay, there is explanation for that. That is because of the specific heat capacity of the substance. Because both of them get heat energy anyway from the sun, from the solar system, but sun is hot, water is still cold. One of the reasons that can be explained there is that because of how much energy, how much heat energy a water can absorb to raise the temperature, and how much heat energy a sun can absorb to raise the temperature. That's two different things. Okay? So the sun gets very, very burning, but the water is still cold anyway, because it requires a lot of energy to raise it. Okay, thank you. It requires a lot of energy to raise the temperature of water. That is the principle is actually specific heat capacity.
We're going to have to remember those formulas.
Which formulas?
The ones for the 1,000 days, H1.
Well, that will be given to you, but we did calculations. I remember you guys left a little bit earlier that day, but we did calculations. So is that, for example, I'm not going to ask you what is a calorie per protein, the calorie per gram of carbohydrates, the calorie per gram of fat.
You're going to give us all that.
Yeah, this will be given to you, but you need to do the calculation part. Okay. I think this was 10. We have 10 things. We have 11? Okay, okay. That means we are. It's also important to talk about intermolecular forces, because you might have questions regarding these intermolecular forces. We know two types of bonds, the common two types of bonds that we know, each of us, ionic bond and covalent bond. This is the known bond that when there is interaction between molecules, we have two bonds. Where do we experience ionic bond? Cassie, where do you experience ionic bond? Non-metals and metals. If you have non-metals and metals, you experience ionic bond. Where do you experience covalent bonds? Non-metals and non-metals. Now, but there are something called intermolecular forces. Intermolecular forces. This is the attraction between inside the molecules. Okay? Like in other words, the attraction between hydrochloric acid and another hydrochloric acid. The attraction between one water molecule. How do the water molecules are interconnected to each other? Okay, well that is one bond. That is one bond. But this is called intermolecular forces. Anyways, we call them intermolecular forces. Hydrogen bond. Yes, water is connected by hydrogen bond. Hydrogen bond is a good example for a water molecule. We have a London dispersion force. London dispersion force. We have a dipole-dipole interaction. I don't know there is here, but there is ion-dipole interaction. That, well, maybe here, maybe not. We'll see on the next slide. These forces are existed in ionic compounds and in molecular compounds. Okay, they are connected to the molecules. They are intramolecular forces. Okay. A London dispersion force. What is a London dispersion force? How a London dispersion force is generated? How did it come? Where does that come from? London dispersion. But London is, by the way, last time I told you, it's the name of the person, the name of the scientist who actually developed this theory. And based on that, it's called a London dispersion force. Anybody remember that? What's a London dispersion force? Yes. Yes, it is a London dispersion force actually comes with the unequal distributions of electrons. Unequal distributions of electrons. Now, in an atom, we are assuming that electrons are distributed in a symmetrical way, in equal way, right? Like, say for example, take helium atom. One helium atom is connected with another helium atom. What is the force inside them? Where does that force comes from? Because always when we are thinking about interaction forces, we always think about a positive and a negative force, right? You have a partial positive charge, you have a negative charge. So different charge always makes interaction. But there's the situations that you don't have protons, you don't have a positively charged particles, right? You have electrons, but there is interaction. That is how a London dispersion force is generated. What happens here, I don't know if you have a picture here. Yeah, what would happen here, this shows you an example how London dispersion force between two CH4 molecules existed. CH4 molecule is a covalent bond, and sometimes the electrons distribution on one side will be larger, the electron distribution on the other side will be smaller, okay? Between this CH4 molecule and another CH4 molecule, you have less electron density here, okay? See, this is not like something that we say, but electrons are in movement. If you think about electrons are in movement, 24/7 electrons are in movement. They are not stationary. They are not in one position. And it is obvious that at one point, all the electrons will be on one side, and on the other side, there will be a lack of electrons. That's bingo. That's good. That's like a snapshot. That's like where dispersion force can be created. Because on one side, you have huge density of electrons. That means it is negatively charged. On one side that you have less electron density, that creates what? A positively charged. So now you see between two electrons, between two electrons density, I would better say, you can create opposite charges. That's how the dispersion force is created. Less electron density in one region creates a partial positive charge like here. More electron density in one region creates a partial negative charge. and that creates what? That creates attraction. Now, dispersion force is weaker because it is not really stronger as hydrogen bonding or ion dipole bonding. It's a weaker bond, but there is attraction there. Okay, there is attraction there. It is one of the weakest links. It's one of the weakest bonds of all the intermolecular forces. Whereas hydrogen bonding is stronger. Remember this, hydrogen bonding is stronger. How do we know hydrogen bonding is stronger? You take the boiling point of water. You see, the boiling point of water is 100 degrees centigrade. Okay? The boiling point of ammonia is also greater. Now, hydrogen bonding is what? Hydrogen bonding means it's a bond between hydrogen and some high electronegative ions. That means it's a bonding between hydrogen and oxygen. It's a bonding between hydrogen and nitrogen. And it's a bonding between hydrogen and, oh, I forgot the third one. Chlorine? It was hydrogen and oxygen, hydrogen and nitrogen.
Chlorine.
No, it's not chlorine. It's not chlorine.
No, not chlorine. The F one, chlorine, F,
Hydrogen and fluorine, yes. Yes, hydrogen and fluorine. You're right. Hydrogen and fluorine. It makes sense because fluorine has a higher electronegativity element. You know, fluorine has the highest electronegativity element. It's 4.0, by the way. So it is a bond between hydrogen and fluorine, hydrogen and oxygen, and hydrogen and nitrogen. And it's a stronger bond. Unfortunately, hydrogen bond is only between the bond of these three elements, between hydrogen and nitrogen, between hydrogen and oxygen, and hydrogen and fluorine. And also there should be, the other requirement for hydrogen bonding is that there should be also what? A lone pair of electrons available. Lone pair of electrons, okay? So a lone pair of electrons, which is unpaired electrons, and also they are ready to react with other ions because they are lone pairs. They need a partner. They need a connection with the other ions. So that's the requirement. The hydrogen bond is a stronger bond. Yes.
I know you said electrons are not stationary. So in this diagram, we have the same amount of electrons on the left-hand side and the same amount of electrons on the right-hand side. So one is one more than the other.
No, if you look at it here, this is a partial positive charge here. These are not electrons here. A partially positive charge versus with a partially negative charge here. A partially negative charge means there is more electron density. Okay, charge of electron is negative. A partially positive charge refers to that there is a less number of electrons. That is the weakest number of electrons. Okay, so it's not a plus sign is an indication that there is less electron density in one region. A minus sign indicates there is more electron density. So that actually creates inducing, that creates a force. And that force, it's not the same thing as electronegativity. This is the same atoms, the same electrons. Okay, now, now we say helium has 2 electrons, but the reality helium doesn't have 2 electrons. Honestly speaking, helium has billion number of electrons. Okay, for a systematic reason, we just count the outermost shell electron, but there are like billion number of atoms of electrons. So on one side, a huge density of electrons will be on one side, a less density of electrons will be on the other side. To understand this, that's how it is. So this kinds of theory is better explained in quantum mechanical model of an atom. We all learn a Bohr model of an atom. Atoms have 2 shells in the first electron, 8 shells in the second, 8 electrons, to 18 electrons, and our mind is concentrated only with fixed number of electrons. Honestly speaking, that is wrong. That is false. Because electrons are not counted. Okay? You have densities. You have electron density. That is a good way of explaining, for understanding, just to create interaction. But the truth of the matter is lie beyond that. Beyond that. Okay, we have hydrogen bonding here. You know, hydrogen bonding is like water is, remember this? Let me ask you on the test. Hydrogen bonds are the strongest of the three types of intermolecular forces.
Did you explain this slide 12?
Okay, here is here is a dipole-dipole interaction. A dipole-dipole interaction exists as the attractive between permanent dipoles of two polar molecules. Okay, what's dipole-dipole interaction? Let's say that you have a formaldehyde here. Okay, you have CHO here. One CHO is here. We have oxygen is here. And then we have carbon is here. Carbon has, it is an attraction between the same molecules. Okay? Dipole-dipole interaction is going to be an attraction between two molecules. Now, how this happens, there are two things I want you to be focused on dipole-dipole interaction. One, orientation. Orientation. So orientation is the molecules have to be oriented. The oxygen end has to be connected with the carbon in here because oxygen has a partially negative charge. A carbon has, compared to oxygen, a carbon has a positively charged particle. So there is interaction between these two. What is the intensity? What is the strength of interaction? That's another question. But there is intermolecular interaction anyway. Okay? That's a dipole-dipole interaction.
How do you know if it's a negative or positive?
There's a lot of things that you should know. One of the things is that think about the periodic table, generally speaking. Electronegativity increases from left to right. Generally, right? So if I have carbon and oxygen in this case, okay, I can guess which one has a higher electronegativity, which one has a higher which one has a higher electropositivity. Okay, now if it comes carbon and oxygen, without even remembering or noticing the number, I can tell you oxygen has a higher electronegativity than carbon, because oxygen is on the right of carbon in the periodic table. Now, you may have a situation between nitrogen dioxide and nitrogen dioxide. The interaction between nitrogen dioxide and nitrogen dioxide. Now, we know for sure nitrogen is a non-metal. Oxygen is also a non-metal, right? Compared to nitrogen and oxygen, one has to be more electronegative. The other has to be less electronegative. So I would conclude, or I'll give you a summary that nitrogen has a positive charge than oxygen. Am I right or wrong? What's that?
I'm the one making up the midterm for what I
Okay. Nitrogen has, which one? Is it nitrogen or oxygen has a higher electronegative? Oxygen. Oxygen. Why? Because oxygen is located what? Oxygen is located on the right. So a partial negative charge is on oxygen, and a partial positive charge is on what? On nitrogen.
So the further to the right, it has negative charge, and to the left, it has a positive charge.
Positive charge, yes. Now, in this case, for example, in formaldehyde, it is an organic compound, unsaturated organic compound. We have oxygen and carbon.
So even non-metals can be positive?
Yes, relatively.
Okay.
Now, don't take this in words. Positive means that there is less electron density there. Okay, there is more electrical attraction, there is more electrical attraction on oxygen side. There is more electron on oxygen side, so there is high electron density on oxygen side, less electron density on nitrogen. So there is a dipole-dipole interaction between nitrogen dioxide, right? A dipole-dipole interaction. So that is exactly what it means. It's 103, right? A 101? Yes. Oh, okay. Well,